students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. This is lecture number 5. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. Okay. So, in this lecture we are going to start a very useful topic when it comes to semiconductor devices. We are going to start the concept of carrier transport in these advanced devices. Okay. So, till now we have focused our discussion on two things, mainly charges and the concentration of charges. Okay. So, we have tried to explain that a semiconductor whose conductivity is generally tunable via doping, you can control the number of charge carriers which are present in your devices. Okay. So, we have calculated the electron and hole concentrations in the conduction band as well as in the valence band. Okay. So, why we have done that? See, all the semiconductor devices, or for that reason we can use the word electronic devices also. These devices have a primary objective of generating appreciable amount of current for any applied voltage. Okay. And when we are talking about current, we are interested in charge also, and charge is produced by two types of charge carriers in semiconductor devices, mainly electrons and holes. So, we have calculated so far how many electrons are available per unit volume in the conduction band, which is your electron concentration. Okay. So, if you remember the equation, we denote electron concentration by N, and it is given as Nc, which is the effective density of states in the conduction band, exponential minus EC minus EF by kT. EC is your start of conduction band, EF is the Fermi energy level, K is Boltzmann constant and T is temperature. Okay. So, these are the number of electrons per unit volume available inside the conduction band. Now, these are the electrons which will contribute to current. Okay. Similarly, we have also calculated the hole concentration. It is denoted by P and given as NV exponential of where NV is effective density of states in the valence band, EF again Fermi energy level, EV is the end of your valence band, the top energy level of your valence band. So, these are the number of holes which are available per unit volume inside any semiconductor device. Now, we know how many charge carriers are available to this. The knowledge of this carrier concentration is quite important, so that we can understand the electrical properties of the device. Okay. The net flow of these charge carriers only. So, electrons in the conduction band, holes in the valence band, the net flow of these charge carriers in a semiconductor is what is going to generate current. The process by which these charged particles move is called transport. Okay. That is the main topic which we have, the carrier transport. Okay. So, the process by which these charged particles, these electrons and holes, the way they are moving, that is known as the phenomena of carrier transport. This is a vast topic, we are going to divide it into small parts only, okay, so that we are able to understand it completely. Let us continue our discussion. So, when we talk about carrier transport, now when you compare semiconductors with metals, metals only have electrons, freely available electrons, you apply a small voltage and they start to drift. Insulators do not produce any current, so there is not a lot of question of thinking about carrier transport in insulators. But when it comes to semiconductors, the phenomena of carrier transport has lot of components associated with it. Okay. Broadly, there are two transport mechanisms which are in a semiconductor crystal, mainly drift current and diffusion current. Okay. Drift current happens. So, the total current density, now when we are talking about currents inside a semiconductor, we do not talk about absolute value of current, say in milliampere or microampere or amperes. We generally tend to describe the conductive nature of a semiconductor in terms of its current density. Okay. Current density by definition is current per unit area, right. So, because we are talking about subatomic particles, which are not visible. So, when we want to count them, we count them per unit volume via concentration, and when we want to study the amount of current, we study current density, which is how much current is produced per unit area. Okay. So, the total current density inside a semiconductor will have two components. Okay. It will have drift as well as diffusion. Okay. So, I will use these subscripts drift for, or I can say use dr also. Okay. So, these subscripts basically tell you the individual components of current. Drift current usually happens whenever there is an electric field present across a semiconductor. Okay. Now, the phenomena is, the requirement is the presence of an electric field. If you apply a voltage across a semiconductor of finite length, you are basically applying an electric field only. Electric field is voltage gradient, right. Even if you do not apply any external electric fields can get induced or develop on their own inside a semiconductor, right, and those electric fields which are induced may also be able to produce drift of charge carriers. Okay. So, the important point to understand here is that whenever there is a presence of electric field, whether extrinsically applied or whether intrinsically available, the presence of an electric field inside a semiconductor is going to result in some kind of a drift current. Okay. Another mechanism of current inside your semiconductor is the diffusion current. Whenever there is a concentration gradient, right. So, diffusion in general is a process where a particle or molecules or something flows from a higher region to a lower region, and when we are talking about these doped semiconductors, we are talking about the gradient of the concentration. Okay. So, if you have higher electron concentration spatially with respect to distance between 2 points, you can have diffusion current with charges flowing from higher concentration to lower concentration. Okay. So, diffusion is always going to occur from a region of higher to a lower concentration, and it is going to happen for both electrons as well as holes. The total current, as I have said, is the sum of drift and diffusion current, and within drift and diffusion current, since you have two types of charge carriers, okay, many semiconductor devices are bipolar in nature. When I say bipolar, I mean those devices which have conductivity because of two types of charge carriers, both electrons as well as holes, right. So, this drift current by itself can also have a component because of electrons plus a component because of holes. Okay. Similarly, the diffusion current can also have contribution from electrons, okay, as well as contribution from holes. So, when we are studying carrier transport, not only we want to understand the mechanism which is producing this conductivity, at the same time when we want to mathematically quantify the current density, we should need the individual components also. Okay. So, broadly you are going to have two types of current components. Okay. You can have drift, and drift can be because of both electrons as well as holes. So, you can have electron drift current and you can have hole drift current. Okay. At the same time you will have diffusion current, and that can be because of electrons also. So, you can have electron diffusion current and you can have hole diffusion current. Okay. Not necessarily that every semiconductor device will exhibit bipolarity. We do doping, we sometimes deliberately increase or try to tune the conductivity. It is possible that one type of charge carrier dominates over the other. As we know, in N type devices, electrons are very large in number as compared to holes. In a P type device, holes are very large in number as compared to electrons. So, it is possible that in a particular device, you might have one type of charge carriers dominating over the other. Okay. But this is a holistic equation which includes all the components. So, you might have that in an N type device, only the N type drift and N type diffusion current dominates, and the other two components are so small that they can be ignored. In a P type device, the whole drift current and the whole diffusion current can dominate, such that the electron current becomes very negligible. So, in that case you can ignore that current also. Okay. But if you want the complete value, the whole value, you will include both drift as well as diffusion, you will include electron and hole diffusion current, you will include electron and hole drift current also. Okay. So, this is the start for our carrier transport topic. So, let us discuss about drift current in detail. As I have said, drift current only occurs whenever there is a electric field present. Okay. So, suppose you have a semiconducting material, you have a large piece of semiconductor, it has say some n number of charge carriers you can have, it has a certain length L and you apply a voltage across it. Okay. For starting discussion, let us say that this is an n type semiconductor. Okay. So, this is n type and it has n number of electrons present inside it, because I have said n type. So, lot of electrons are going to be there. So, I can for now ignore the whole component, okay. But the discussion is equally valid for a p type semiconductor also. So, if I apply an electric field across it, so if I have applied a voltage V, it means I have applied an electric field equal to V by L. Okay. So, this is the magnitude of electric field which is acting across this semiconductor, voltage divided by length. Whenever you apply this electric field, now what is going to happen? You are going to create a potential difference across this semiconductor. The electrons start moving from the negative to the positive terminal. Okay. So, electrons move in this direction and current starts to move in this direction. Okay. We already know that the direction of current is opposite to the direction of electron movement. Now, these electrons are going to collide with other electrons, they are going to collide with ions, defects, other atoms, okay. But generally there is going to be a net motion from this negative terminal to this positive terminal for electrons. We can say that electrons are drifting in the presence of an electric field, and this drift produces what is known as drift current. Okay. The net drift of these charge carriers move or gives rise to drift current. Holes move in the direction of electric field from positive to negative, while electrons drift in the opposite direction of electric field, that is from negative to positive. Okay. So, whenever there is an electric field present, we see a drift current. Electron drift current and hole drift current are opposite in directions, because holes and electrons move in opposite directions. Okay. While drifting, as I said, these charge carriers collide with what they can collide? They can collide with other atoms, ions, the heavier particles which do not move, okay. With other charge carriers also, some defects in the material. Okay. So, there are continuous collisions also. When electrons are drifting from negative to positive electrode, there are constant collisions inside the semiconductor material. Okay. After a certain time, a constant equilibrium is reached. So, I can say that a constant drift velocity has been achieved under the presence of an electric field, which is say constant and at a reasonable value, I would say low to moderate value, I would say that a constant drift speed has been achieved. What force is acting on the charge carrier? This is the force which I have applied via the electric field. The applied electric field is providing a force to the charge carriers, to the electrons. This force is equal to Q times E, okay, because we know that electric field by definition is force applied per unit charge. Whenever you apply an external electric field via an external bias or voltage, you can say that a force per unit charge has been applied. This is your applied electric field. Okay. So, this is the force which is acting on the charge carriers, and this is the electric field. Okay. So, I can say that a force equal to Q times E has been applied. By Newton's second law, I also know that force is equal to mass into acceleration. So, these particles which are under the influence of some kind of a force, they would be getting accelerated. When they are drifting, they are accelerating from one electrode to another electrode. Okay. So, this force is also equal to m times a, but if you remember in one of our initial lectures, we had discussed the concept of effective mass. Because of these constant collisions, there is some loss of acceleration also, but the applied force is constant. So, if applied force is constant, because I am not applying a variable DC supply, I have applied a constant voltage. So, if I applied a constant force, if my acceleration is not say constant or it has a certain average value, okay, because of all these collisions, to account for that loss in acceleration due to charge due to collisions, I introduce the concept of effective mass. Okay. So, instead of free mass, we use the carrier effective mass. So, applied electric field Q times E equal to m dot A, instead of m we use m star, which is represents the carrier effective mass. Okay. This equation I can write as F equal to m star effective mass into, instead of acceleration I have replaced it with the definition of acceleration, velocity upon time, and when the charge carriers are drifting, they are drifting at a constant speed. Okay. Would not say constant speed, would say that an average speed has been achieved, right. So, this speed or this velocity which we are talking about is known as the drift velocity, the velocity with which charge carriers drift in the presence of an electric field. Tau is the mean relaxation time, that is the time between successive collisions. Okay. So, this is the force acting on the charge carriers in the presence of an electric field. These two equations, okay. So, if I continue with this equation, I already have this here with me. So, I can equate these two, I can equate 1 and 2, right. If I equate 1 and 2, I am going to get Q dot E, okay, equal to this V d by tau, okay, which means my drift velocity is proportional to electric field. Okay. And what is electric field proportional to? It is proportional to how much voltage I have applied, E equal to V by L. Okay. So, depending upon how much voltage you have, external voltage which you have applied across the semiconductor, you can decide how much electric field is present across this device. Okay. So, I can say that the velocity with which these charge carriers are drifting, okay, the velocity at which these charge carriers, electrons from negative to positive terminal, holes from positive to negative terminal, how they are drifting, that drift velocity is directly proportional to the electric field. Now, this relationship of V d drift velocity being directly proportional to the electric field, always keep in mind that this relationship is valid till moderate values of E. Okay. At very high electric fields, we are going to see later on that at very high electric fields this relationship does not hold true, but for now for the discussion of drift current, we can safely say that the drift velocity, the velocity with which the charge carriers are drifting, is directly proportional to the electric field which has been applied across the semiconductor, and the constant of proportionality is this. This is your constant of proportionality. Okay. So, if drift velocity is directly proportional to E, this term here is my constant of proportionality. Okay. And what is this term? This is equal to mu or represented by mu and is known as the mobility of charge carriers. Okay. We have seen in the energy band topic that the mobility by itself can or the effective mass depends upon the energy band structure. The curvature of energy band diagram basically decides the value of effective mass. Okay. So, higher the curvature, steeper the energy band diagram, lower will be effective mass, which means in such devices you are going to have high mobility, and mobility by definition is a parameter, is a physical parameter which measures the ease with which charge carriers move inside a semiconductor crystal. So, whenever you apply this field, how easily charge carriers can move inside the crystal is decided by the mobility of that material. Now, you would know that not every material is going to produce the same amount of current, not every semiconductor is going to allow flow of charge carriers in the same way, there are going to be certain differences. there are going to be differences in the relaxation time, there are going to be differences in terms of effective mass, right. When these parameters are different, it means mobility is different, and if mobility is different, the drift speed is going to be different. Okay. So, this is the concept of mobility. If I now need an expression for drift current, I am going to start, say this is a piece of semiconductor. Again my discussion is for n type, I will give you an example for p type also. So, this is an n type semiconductor. Okay. It has n number of electrons, this uppercase n tells you how many electrons are there. This is not the concentration, this is the absolute number of electrons. Okay. So, if I want to get the electron concentration, I will have number of electrons. Okay. So, I will use number of electrons divided by the area times length, number of electrons per unit volume, this will be my concentration. Okay. So, a piece of semiconductor n type, length L, area A, total number of electrons is n. I want an expression for the electron drift current density. By definition, your electron drift current density is current per unit area, that is how we define drift current density. Okay. Current we know is charge upon time, you already have area here. Okay. So, drift current density equal to, by definition, current upon area, current by definition is charge upon time. How much charge is flowing? If there are n number of electrons, the charge is going to be minus q times n. Why minus? Because electrons have a negative charge. Q is the charge of one electron and n is the total number of electrons. So, that is the amount of charge which is flowing. The amount of charge which is flowing, how much time it is taking? For time I have replaced it with a distance. So, if this is the drift velocity, velocity is distance upon time, how much distance these charge carriers are travelling? They are travelling length L, okay, across some time they are taking. Okay. So, they are taking some time, and this time I have replaced with L over V d. Okay. So, instead of time I write distance and I write the speed, okay, and area is represented by A. So, if you see this term here, this is nothing but number of charge carriers, number of electrons per unit volume. By definition, this is the electron concentration, okay, represented by lowercase n. Okay. So, this is my electron drift current density. Okay. And I already know that the drift velocity is proportional to electric field, constant of proportionality is minus mu n, is mu n. I use this minus sign, this negative sign is because the drift of electron, or I should say V d, is opposite to E. Okay. So, when electrons are drifting from the negative electrode to the positive electrode, the drift the electric field applied is from positive to negative, and drifting of electron is from negative to positive. So, the directions are opposite. So, there is a minus sign here. Okay. So, initially I had this equation, okay, and I also have this equation. These two equations I combine and I come up with an expression where I can say that the electron drift current density is equal to this n q mu times E. Okay. N electron concentration, q electron charge, mu n mobility of electrons, E is the applied electric field. Okay. And this term here which you see n q mu n is basically the conductivity of charge carriers. Okay. This is the electrical conductivity or electron conductivity. Okay. Why electron conductivity? Because we have electron current density and you have electron mobility. Okay. Similarly, for holes we use the same concept. The hole current density is equal to current per unit area, current again charge upon time. Okay. So, instead of n number of electrons, now I have n number of holes. L times A is the volume. Okay. So, n by L times A is going to be the hole concentration. Okay. And drift velocity I can write as hole mobility times electric field. Now, there is no negative sign here, because holes move from positive to negative, electric field applied is also from positive to negative. So, there is no negative sign. Okay. So, hole drifting, hole drift current and applied electric field are in the same direction. Combine these two, okay, this should be J dot P here. Okay. Again I think I have put the wrong subscript, this should be J P. Okay. So, with this the whole current density, if you combine these two equation, you are going to get this third equation. Whole current density is Q dot N mu P times E L times A, which is nothing but N by L into A is the whole concentration, charge Q, mobility and electric field, and this term here is nothing but the whole conductivity. Why this is conductivity? Because see, it is taking the concentration, charge and mobility. All these parameters basically tell you how conductive the material is, right. So, if I combine these two equations, the total drift current in a semiconductor is produced by both electrons and holes, right. The electron drift current is sigma n e, hole drift current density is sigma p e, sigma is n q mu n for electrons, p q mu p for holes. So, this is the total drift current in a semiconductor. In an n type devices, obviously electron drift current will dominate, in a p type device the hole drift current is going to dominate. Okay. So, this is your complete drift current density J equal to sigma E. A small topic here which is related to resistivity, which is nothing but the reciprocal of conductivity. Okay. So, these are some of the references which you can refer to for this lecture. Okay. And with this we come to the end of today's lecture. We have started the topic of carrier transport and we have discussed the topic of drift current density for both electrons as well as holes. Okay. Thank you.